Hi, my name is Raymund Ubaldo. And today, we will present our project, which will be focusing on the Project 1 of harvesting a renewable resource. So, background of the problem. So, for our background of the problem, renewable resources refer to resources that can be used repeatedly and does not run out since it is naturally replenished. There is a continuous increase of the demand for natural resources because of growth in human population, and if resources are not managed properly, it can cause global starvation, extinction of species, and human instability. One of the main sources of food is fishery, and it is important to maintain the fishes caught with its population to have stability without endangering the species. So now for the statement of the problem. The focus of the study will revolve around explaining the renewable resource of fish through the use of differential equations. The logistic equation for the population y of any species of fish in a certain area will be described by the equation of dy over dt equals r parenthesis 1 minus y over k times y. With the concept of harvesting in the population equation, it will be remodeled applying the rate of harvesting members per unit time, which result into the equation of dy over dt equals r times parentheses 1 minus y over k times y minus the rate of harvesting. So from that, we would apply it in answering problems about constant effort harvesting and constant yield harvesting, utilizing differential equation concepts and with the help of the MATLAB program for running through the problems and visualizing them. So here are the solutions to the problem using DE concepts and MATLAB.
Hi, this is Jericho Villanueva, and I will be the first sharer of the problems and solutions, specifically the first parts A and B. Harvesting a renewable resource. Constant effort harvesting. This method usually describes that the rate at which living beings are removed from its population is dependent on the current actual population of those living beings that are existing. And this was introduced with the help of Milner-Bailey-Schaefer, which thus also formulated the Schaefer method. In this case, we have that dy over dt is equals to r, open close parenthesis, 1 minus y over k times y minus ey. Moving to the first part of the problem, problem A, show that if E is less than R, then there are two equilibrium points, which is y1 is equal to 0 and y2 which will be equal to k, open close parenthesis, 1 minus E over R is greater than 0. So by equating it to 0, we have already found the first point. And from that point, just also left us the R open close parenthesis y over k minus E equals 0. And we are basically finding y, which leads us into these two equilibrium points. y1 is equal to 0 and y2 is equal to k, open close parenthesis, 1 minus E over R. Now, to the second part, part B, show that y is equal to y1 is unstable and y2 is asymptotically stable. So let y is equal to 0. If y is less than 0, then r open close parenthesis y minus ey is less than 0. And if y is greater than 0, then r open close parenthesis y 1 minus y over k times y minus ey is greater than 0. And this can be represented by this illustration, which gives the conclusion that y equals to 0 is an unstable equilibrium. Now to the next point, if 0 is less than y, then y is less than k, open close parenthesis 1 minus E over R, then dy over dx is greater than 0. And if y is greater than k, open close parenthesis 1 minus E over R, then dy over dx is less than 0. And this can be represented by this illustration, which gives the conclusion that y2 is asymptotically stable equilibrium. Now let's utilize MATLAB capabilities to compare our answers. So we are already here in MATLAB. Moving to the first part, which is fairly simple since we are only asked to find the two equilibrium points. So first let us create and set our symbolic variables and functions, which is this and this. And if we run the code, it will give the two equilibrium points, which is similar to the first that we have already taken, which is 0 and kr minus ek over r, which is totally the same as the k times open close parenthesis 1 minus e over r itself. Now moving to the second part, we are only asked to plot a function wherein we can somehow visualize the unstable part and the stable part. So if we run the code, this will show this graph. So as we can see, plotting the function itself versus the set of points that have been set, which is r is equals to 2, k is equals to 1, and e is equal to 1. You see that the equilibrium at y0 is unstable, and the equilibrium at y is equals to k over open close parenthesis 1 minus e over r is stable, which is here. So that's all. And hence, with these problems, through harvesting, if there is a very high population, it will eventually result in a decrement of the population itself. So the population will decrease until it will reach a sustainable equilibrium. If the population is moderate, it will also eventually result in an increment of the population, and hence the population will reach the sustainable equilibrium state. But if the population in the graph reaches negative numbers, in actuality, the population reaches the level of extinction.
Hello, good day po ma'am. I am Eliezer Nitro from OL51 Mat 156. For problem constant effort harvesting part C, a sustainable yield Y of the fishery is a rate at which fish can be caught indefinitely. It is the product of the effort E and the asymptotically stable population Y sub 2. Find y as the function of the effort E. The graph of this function is known as the yield effort curve. To solve this problem, consider first the equation y equals ey sub 2. Since the fish can be captured indefinitely, the solution for y must always be non-zero positive. Thus, the limit as t approaches to positive infinity is y greater than 0. Yet, we know that for all positive solutions, the solutions will develop to y equals to e multiplied to k, then multiply again by 1 minus e over r, close parenthesis. Then look for asymptotically stable solution for y sub 2, which is y sub 2 equals to k multiplied by 1 minus e over r, close parenthesis. Therefore, sustainable yield for y becomes y equals to e multiplied by k, then multiply again by 1 minus e over r, close parenthesis. And if we are going to simplify it, the result would be y equals to ek minus e squared k over r. Since the equation is quadratic, we will expect that the graph would be a parabola up and downward, and that is the yield effort curve. For part D, determine E so as to maximize Y and thereby find the maximum sustainable yield. To solve this problem, consider the result of sustainable yield, which is y equals to ek minus e squared k over r. Then find its derivative in terms of d over de, thus having k minus 2ek over r equals to 0. Therefore, from the equation, we can get the maxima for sustainable yield, thus having E equals to R over 2. Then substitute E to the equation of sustainable yield, and the equation would be Y equals to K multiplied by R over 2 minus K multiplied by R over 2 squared over R. Then cancel R squared to get Y equals to K multiplied by R over 2 minus K multiplied by R over 4. Therefore, simplifying the equation will give us Y equals to 1/4 KR, and this would be the maximum sustainable yield. As we thoroughly analyze the graph, we can observe easily that in order to maximize the value of Y and determine the maximum sustainable yield, we have to see at the effort axis and value at 0 and R. Since the graph is quadratic, the maximum sustainable yield can be located at the midpoint between 0 and R, which is, in this case, is R over 2.
Good day. Next, we're going to solve problem number 2, letter A. So, without further ado, let's get started. So, in problem number 2, letter A, it is constant yield harvesting is the scenario. So, in the problem, we assume that the fish that are caught at the constant rate H, independent of the size of the fish population, that is the harvesting rate of H of YT is equal to H. Then Y satisfy dy over dt is equal to R of 1 minus Y over K times Y minus H, which is then equal to F of Y. The assumption of a constant catch rate H may be reasonable when Y is large. Remember, if Y is large, but becomes less. So when Y is small. Next slide. So in letter A, if H is less than R K over 4, the problem wants us to show that equation number 2 has two equilibrium points, y1 and y2. Equilibrium points are found by setting first dy over dt into 0 and then solving the resulting equation for letter y. So here we have dy over dt is equal to r of 1 minus y over k times y minus h. The previous equation here on slide 1, ry minus r of k times y squared is equal to h. And then the final simplified form is y squared minus ky plus hk over r is equal to 0. So in order to find y, we need to adjust the equation into the quadratic formula. Why? Because in the previous slide, we have here y squared as our a, or the first term of the equation, or the simplified equation rather. So we have here now is y is equal to negative k positive negative square root of k squared minus 4kh as our 4ac over r, that all, and then all over 2. So therefore we can yield y1 negative k plus square root of k squared minus 4kh over r all over 2. Same is true with y squared, y sub 2, but the sign has changed into negative or minus. Lastly, it is said that there will be an equilibrium if the following were to be maintained. So what were to be maintained? K squared minus 4kh over r should be greater than 0. So equate that to 0 first. And then for KH over R must be less than K squared. So K squared has to be bigger. Lastly, RK over 4 should be less than the letter H or the value H. So if these are met in the quadratic equation, and then therefore we can yield the value of y.
Hi, good day. I'm Dave Darren Calangi and I will explain the D segment on constant yield harvesting. Here, the equation H is greater than R, K over 4, where H represents constant catch rate, R for fish growth, and K for environmental capacity, shows a graph where the Y values are plotted under the Y-axis, which also results to tend the arrows are pointed to the left, where it means a decline in the fish population. In this problem, the values for H, R, and K are set to 3. After running the equation in MATLAB, it produces a plot where it shows that the value of fish population is approaching to 0. Observing the plot, this shows a condition where regardless of the fish population, extinction will be done due to overfishing.
So for the interpretation of results, in constant effort harvesting, it simply indicates that it will take less effort to fish if the population of fish is big enough. It also shows that there is a maximum point where we can assure sustainability with the amount of effort given to harvesting. In constant yield harvesting, there is a limit amount of fishing within an area, wherein exceeding the equilibrium will result an unstable relation with the population of the fishes as time goes on. There is a certain rate of harvesting that will be recommendable, which will maintain the source to not easily consume to avoid shortage of fish or in worst case, extinction of them, which could later on lead to not only destruction of ecosystems, but also starvation of people. So for the conclusion, differential equations can be applied to management of natural resources to determine the rate of harvesting a certain renewable resource. This way, environmentalists and economists would easily control the production of food due to the data gathered from using the differential equation model. Mathematical models like this would help explain and analyze the behavior of resources while being massively consumed. That will give support to environmental, ecological, and financial ideas. This would ease the conservation of resources, wherein the source can fully provide to fulfill the needed supply without risking too much loss of it.